talk.
So this is a collaboration with my student Yuki, and I will talk about rotating a stratified flow confined in a cylinder. There's two topics. One is flow confined in a spheroid with velocity field proportional to the coordinates, linear in coordinates. And the question is how and why our rotation can sustain heavy fluid on top of light fluid. And much simulation was given by the book, the late Professor Dozhansky, translated by Boris Hishin. And there's an exact solution of Euler flow in Bushnell's approximation of the stratified flow confined in a spheroid. And we start from the yes, constant density and the perturbation density, and this is confined in the spheroid. Then this continuity equation becomes this form. Q is a gradient of the density perturbations. Then Bushnell's approximation for the velocity field is written like this. And if you take a curl of Euler equation, you have a vortice equation. And this comes from the baroclinic term. And then we call this baroclinic torque. Then you will easily find these three steady solution of this Bushnell's equations. Then by substituting this form, you can pursue unsteady flow. Now I, coming to the next slide, is inertia moment. And capital omega is actually vorticity, and omega k is the coefficient is basis of velocity field. Then you can find this Bushnell's equation becomes the equation for governing this coefficient, and this takes the form of the Euler-Poisson equation governing the heavy top. And m is in the context of a rigid body. M is angular velocity viewed from the coordinate frame fixed to the body. And omega is angular velocity vector. And L0 is now the fixed, because L0 is a vector from the fixed point to the gravity center. And from the coordinate frame moving fixed to the body, then gravity direction is now time dependent, and sigma is the direction of gravities. And in the context of stratified fluid, sigma is a measure of the gradient of density changes. And alpha 1, alpha 2, alpha 3 is angle from the vertical axis of the each coordinate axis fixed to the body. Then when density is only changes in the vertical axis, then gravity center is along the central axis. But you can find a strange model. For instance, you may take two lengths of the same axis of spheroid. Then you have a symmetrical ellipsoid, and this is spheroid. But by choosing the angle of this principal axis from the vertical axis is some finite, then this is equivalent to shift the center of gravity to not along the coordinate, along the axis, but this other directions. Then you have the model with just usually a symmetric top has with center of gravity on the symmetric axis, but now center of gravity is off axis, yet symmetrical top. Then you can find a new steady state. This is a steady solution of Euler-Poisson equations. This one steady solution, and this corresponding gravity central direction is this ways. And when A3, this is positive, it means the density increases upwards. Then this is unstable stratifications. And when stable case, density increases downwards. And we have interest in the stability of the unstable stratified case. And you can make stability based on this ODE. And prorate case is this symmetric axis is longer than other vertical planes. In such a case, this I1 first inertial tensor is larger than the others. Then you can get this growth rate of the steady state. And when phi equals 0, this is well known as stability of sweeping top. And if rotation speed is lower than this critical velocities, then rotating top just break down. But if the rotation speed is greater than these values, then this top can stably rotating. And by increasing these inclined angles, then stable region increases. And this is inclination angle is pi over 6 and pi over 4 and pi over 3. This is a progress case, and this is simple. Then oblate case. Oblate case is this symmetric axis is shorter than the rest of axes, like the beads of Go. Then stability diagram is a little bit strange, and there is two regions. Omega 3 is a rotation speed, and if rotation speed is faster than this, then heavy top can stand up, and then instability starts, and then at this moment, some critical point reaches, and this growth rate diverges. Then another unstable region approaches, and there is a stable region around this. And I think this is a bit strange, but depends on the way of normalizing the coordinates. Then using this knowledge, we can go to the problem of the two different fluids. Light fluids sustain heavy fluids. Usually, this is unstable by Rayleigh-Taylor instabilities. But if you may apply, you can sustain heavy fluid on top of light fluid. Chandler Segal says rotation does not affect the instability or stability from the, I think, energy viewpoint. But as we saw from the gyroscopic effect, rotation can stabilize this. Actually, simple analysis of linear waves says rotation can stabilize. This is just dispersion relation of the infinitesimal wave just given to the continuously stratified fluids. And n square is a Brand biseral frequencies, and n square is positive means density decreases upwards and stable. And f is rotation speed. And without this term, when n is negative, it means heavy fluid is on top of light fluid. This is negative and instabilities. But by applying rotations, this dispersion relation says omega becomes square, become positive, and omega become real, and neutral stability waves occurs. It says when F dominates, then this is, maybe this is better. When this 3D, KL is a wave number in the XY planes. If there is a short waves in this XY directions, then instability may occur. But longer wave can be stabilized by applying rotations. And actually, there is a recent experiment. Oh, sorry. I cannot see this experiment. This experiment shows there's no rotation, and by applying higher rotations, this heavy fluid, without rotations, heavy fluid is unstable. But by applying rotations, this density separation can be maintained at a longer term. This experiment was made by Scarce in 2015, and hinted by this, and also hinted by their analysis, we applied following analysis. Just confine the two fluids, like heavy fluid and lighter fluid, under the lower half of the spheroid, and then you can first obtain the steady state. This is written by this, and apply the rotation. Now, spheroid is upright. Symmetric axis is parallel to the vertical axis. Then linear perturbation analysis is made, and zeta is just elevation of the interface, and this is velocity perturbations. This is well known in the textbook, like Greenspan, and pressure perturbation is written, and this potential is governed by this. Then you can apply the kind of harmonic analysis, and actually, maybe boundary condition is this is no flow through the normal to the boundary, and also continuity of pressure and the kinetic boundary condition applied. And we make variation analysis by applying the minimum condition of the energy functional, and using simple test functions, you obtain the approximate dispersion relations. And this time we get only the result of the axiomatic mode. We need all the mode, but axiomatic mode is only available. And parameter delta caret is a ratio of the semi-axis of the symmetric axis and the rest. And we assume the rotation speed is small in this sense. And atomic number is defined by this. And if we consider -1, it means lower fluid is low to 0, and the upper fluid is 1. Then we apply, calculate this, and compare with the case of cylinder. A cylindrical case was analyzed by Scarce, and we considered spheroid. And when in the case of oblate spheroid, this is a flattened spheroid, and if this semi-axis ratio is 4/1, then this is if rotation speed is greater than these values, then stability is obtained. But if rotation speed is greater than this, instability comes. And this is a spheroidal case. And in cylindrical case, the result is obtained just finite length cylinders. And we compared with the same ratio of the cylindrical case, and the result says oblate spheroid is more stable than finite cylinders. And the case of the ratio of the axis is 2 and 1 is this. And again, oblate spheroid is more stable than cylindrical case. But for parallel spheroid, it's elongated cases. Cylinder and spheroid does not differ much. And this is just an overview. And we can find how spheroid can be the difference of the aspect ratio is understood from the view of the previous case by comparing with the stability of top. This is a criterion of the stability of sleeping top. And if A is a principal inertia tensor in the plane is large compared with principal inertia along the axis, then instability occurs. And this means A is smaller, get more stable with slower angular velocities. And this consistent with oblate spheroid is more stabilized than parallel spheroid. And this is conclusions. And we considered two problems. One is linear flow confined in the cylinders, and we get analogy with a symmetric top, but gravity center of this symmetric axis. And using this analogy, we try to understand Rayleigh-Taylor instability stabilized by the rotation. Thank you very much.